Well, well. I know it has been a while, but I do not come empty-handed. As I said before, that I would get a. Oh man, it's kind of hard to write on this. Right. So we now have a drawing tablet we can work with while we are doing the series. Just every series from now. Uh, so let's get situated. Right, where did we leave off? Um, do, 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 do. Gotta do like the brush. Okay. So can I? Oh, I can. Let me. Can I just use this for everything? Minimize, minimize. Okay, maybe not. Well, okay. Well, this might be better than a than a mouse. Okay. So we were here. We had kind of went forward in the calculus example, but really wanted to come back and really interact with it, right? Really take the time to learn what's going on, break it down on a deeper level than just looking at pretty numbers go by. So right here, let's get started. What's up? No, that went
minus 3x plus 4, then here's
back. All right. First and foremost, let's go ahead and set this up like so. Um, I think I want that, and I want. Oh my lord. Hold on. Let's get this situated. This goes here. This. We'll do this. And we'll do this here as well as the final third. Hopefully you guys can see everything. We'll slide this over. Or we'll do half and half then. We don't need Visual Studio for now. And then this come here like so. Wonderful. All right. And let's go ahead and make that a bit more like that.
our code
Good.
from earlier
Wonderful.
for
Awesome.
approximating and drawing the slope of a function, and we just want to figure out a more efficient way to calculate the slope, where we don't need to call the function multiple times. So let's consider this line first, which I'll write out in more mathsy notation over here. And let's just see where this takes us if we try patiently working our way through the calculation.
Okay. So first we have the first function of y equals x squared minus 3x plus plus 4. Right. And what they're saying here is the change or
And let's just line first, which I'll write out in more multiple times. So let's consider this line first, which I'll write out in more mathsy notation over here. And let's just
so it's saying this is delta. The delta of f or y equals f of x plus h. Let me make this a little prettier, right? Because we're saying the delta of x is equal to f of x plus h minus f of x, right? And so here we can say the delta of f is equal to first, right? First function, which we can look at as this x plus h is going to be x plus h squared minus 3 times x plus h is my understanding, right? plus 4, right? And then you take this entire equation and then subtract it by the x. Let's just let's come here, and then you're going to subtract it by the original equation, which was your minus x squared minus 3x plus 4. Okay. Now we have to expand certain uh, aspects of this. So you're saying first and foremost, you have what are we working with? First and foremost, you have x plus h times x plus h. And then I'm gonna try to remember this, right? It's you have your FOIL rule. So you have your first, which gives you x squared. You have your outsides, which gives you plus x of 8, x times h. You have your inside, which is plus x of h. And you have your last, which is plus h squared. All right, minus, because we're back up here, minus 3x plus, or sorry, minus 3x uh, plus 3h plus 4. And then we have all of that minus the same equation here. Right? So we can just kind of um, minus x squared minus 3x plus 4. Right? So here we have the expanded equation, right? And from here, now let's look at like terms, right? So you have x squared minus x squared. So you can cross these out. You have x of 8 xh plus xh, which should go to 2xh if I'm not mistaken. So you starting with 2xh uh, plus, excuse my writing right now. Um, it's going to get a lot better as we continue. So you have 2, Jesus, all right, hold on. We have, I'm not a perfectionist, you're a perfectionist. 2x plus h, or 2xh plus h squared minus 3x plus 3h plus 4. I assume, no, you can't do that. Okay. This to me looks simplified as much as you can. So let's see where he gets it.
Just see where this takes us if we try patiently working our way through the calculation. First of all, we can write out this f of x plus h in full by just looking at our equation up here, and wherever there's an x, replacing that with x plus h, like so. And then from that, we want to subtract f of x, so let's write that out in full as well. Now, if we want to simplify this, we'll first need to expand it all. So x plus h squared comes out as x
Ah, I see the issue. I did not. Well, we'll see.
squared plus 2xh plus h squared.
What I'm looking at right now is I didn't pass this across the line because technically that would be something completely different. Yeah, let's try this again. Let's try this again just to get it right, right? Um, so if we're really looking at it like more like that, then you're saying it becomes negative x squared plus 3x minus 4, which then you're still crossing this out, but it also opens up the aperture for 2xh plus x of h plus, oh, sorry. It's really early. All right, two, oh, two x a. It's wonderful. All right, 2xh plus h squared minus um 3x plus 3h 3x, and as you see here, it's also the same situation where you're really this, right? It's really minus 3x plus h, so this turns into negative 3x, and then this turns into negative 3h, and then plus 4, because that's outside of the equation. And then we're subtracting, we have the bottom equation here is going to be as well x squared plus 3x minus. So here, it actually changes up a bit because now we can cross out positive 4 and negative 4. We can cross out negative 3x, positive 3x. We can cross out, that's about it, right? X squared. So you end up with 2x h plus h squared minus 3h minus x squared, from my understanding. Um, oh no, this gets crossed out as well because this x, these terms are together. This gets crossed out, which leaves 2x h plus h squared minus 3h. You can get rid of all these h's. Um, so you're getting 2x plus h minus 3, which, wow, look at that. Okay. So it should be 2x plus h minus 3. And that should be the delta between the delta of f. Now, let's sit down for a second and the delta of f finding and something like f of x minus h, and then plus h, f of x plus h minus f of x. I believe, it's minus. Yeah, f of x plus h minus f of x. Delta is the change in function's output. Input changes by delta x equals h. Output changes by delta f. How much the output change when you nudge the input to make it meaningful? You normalize it by the input change, which is funny because that's basically what we ended up doing just mathematically, right? It kind of balances out to where it ends up being this, anyways. The f of x plus h minus f of x divided by h, which we ended up doing. Average rate of change over that tiny interval. Okay. So what happens as h approaches 0, you get the derivative. Finite difference, exact local slope. Um, okay, but so here's what I'm not understanding really is what's the difference between the average rate of change and your exact slope? Because to me, they sound the same, right? If you come here and you say, if you come here and you say, well, there's a function, uh, right? You have a graph and you have this going through a little bit under the origin, and then you have this coming here. If I plot a point here, right? Oh no, it's supposed to be 2 points together. like that, I believe. And then you're getting this slope here, which would be like boom, boom, is my understanding. And then as x approaches zero, this is considered the exact slope. Is that what it is? Because this is here, and then here, let's see, what is the difference between average rate of change and the exact local slope? The slope of a straight line connecting 2 points. The slope of a straight line connecting 2 points. The slope, right? The slope of a straight line connecting 2 points. So to me, these 2 points are connecting. So the slope, though, is just it's a straight line, though, right? So maybe it needs to be more like maybe my example of graph is bad. Maybe it's like this, and then if I'm moving it by h, it'll be like this, maybe, right? And we're saying, okay, what's the slope of connecting these two lines of here and here, right? Is this what they're talking about, right? x of x, the xy coordinate of of graph one, which is here, or let's use here, right? This is the xy coordinate of graph one, and then x plus h, which gets me here, y of x plus h, which is here, is here. That's just this is right. Am I crazy? Am I explain it? To be like I haven't done math in 5 years. Whoa, 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 whoa. All right. So, as always, and now that I do have a tablet, um, I like to draw everything out. I love visuals. I think visualization is key. So, you're driving on a road that goes up and down. Okay. So, let's imagine this is a road up and down, right? And it goes up and down. So, this is your road, and you are driving in a little tiny car, living your life, blasting music, whatever the case. Yep. It's the worst car you'll see today. Put a little exhaust on it. Matter of fact, let's get a spoiler. Let's get some neon head. I'm playing. All right. So, on average, so you look at where you started, which we'll call here, and you look at where you ended. Let's say we end here. On average, how steep was it between those two spots? This is like driving from mile 10 to mile 12, ending up higher, 200 feet higher. On average, the road climb 100 feet per mile. So, what is the average between all of this? All right, if this is one, this is zero, this is back one, then calculate that to give you the average. It's two divided by three, whatever gets you the slope between these two lines, is my understanding. So exact slope is how steep is the road right under my tires. So if I'm here, the slope is here, but if I'm here, the slope is more like this. If I'm here, then the slope is this. If I'm here, the slope is that. There. You stop the car, look straight down. Is the road tilting up or down right here? Okay. 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 That makes sense. So the average change. So the derivative, so the derivative is the slope at this moment, which is found by when h approaches 0. The slope at this, I see. I see. So essentially, we have this graph. Okay, I see. So we have this street, right? Boom, boom, boom. This road. Let's do this again, actually. So we have this road, right? And say we're here. Um, say we're here, and we want to figure out what this slope is. Well, we could find the average rate of change, right, between 2 points on a line. But this is h plus, let's say, one, one, two, three, four, five. This is h equals 5, though, right? But as h approaches 0 back this way, right? Because we're starting from here. Let's say we're talking right here. Yeah, right here. The distance between those 2 points can now be calculated with the average rate of change, and it'll get you essentially the slope of that certain location. Because in order to find slope, right, you need to be essentially looking at two different points. And so by putting those 2 points right next to each other, right, you then in turn find the slope of any given location as h approaches 0. Right? That's bad, but you get what I'm saying. Okay. So in order to find the derivative is just allowing us to find the
Then
okay.
we subtract 3x
The
and 3h.
derivative is just allowing us to find the slope of a certain point.
We add 4, and finally subtract the rest of this stuff. And now we can see that this x squared and this negative x squared will gobble each other up, as will these two terms and these two terms. So once the dust settles, we've managed to simplify things quite a lot, and we can also see that h is a common factor in all these terms, so we could even neaten things up a little. That's as far as we can really take it though, so referring back to our code, we then calculate the slope by dividing this change in the output by the tiny change to the input that caused it.
Mhm.
So let's write that out over here. Right away, we can see that these two h's will cancel each other out, and we're left with just 2x plus h minus 3.
So the top function is the change of y essentially. And you get that by finding y of x plus h minus y of x, right? Because you're saying, right, have a curved road, and you have the y here and the y here, right? And so you're adding to x, you get your slope, right? And that gives you the change of y between these 2 points. Now, to get the change of x, well, we get the change of x we already know is h. So h is the change of x because you're starting technically from zero at this point. You're treating this as zero, and then this is going to be like, say, three. It's off of three. So you already know this is going to be three, right? So then you can just say, well, okay, three, three, three gets crossed out, and that leaves me just with the change between these 2 points. Now, as h approaches zero, when it comes back this way, that calculation is going to get you the direct slope of these 2 points. Because if it's here, this changes the slope. If it's here, that changes the slope. But we want, what are we doing right now, this moment? And it's going to be more like that.
Here's where things get a little weird though. We know that the closer h is to 0, the more accurate our approximation of the slope will be.
Mm-hmm.
We also know it can't actually be 0, because then not only would the change in the output just be 0, but we'd
Uh-huh.
also be trying to divide everything by 0.
Which, oh, which makes sense now because, again, we're trying to find the change in movement, essentially, right? So if it's zero and there's no change in the graph itself, then how can there be a change in movement?
Nevertheless, if our answer over here gets more accurate the closer that h is to 0, it makes sense intuitively at least that we should just remove h entirely. But we don't want to be put in math jail, of course, so let's be a bit careful about this. First of all, we should switch to a proper calculus notation, which looks like this. So this notation up here represents an approximation, whereas this is going to be our exact answer.
Okay.
We can then add this bit
Okay.
of mathematical legalese, which just says as h gets closer and closer to
Okay.
0, this
So we're not actually, so by doing this, you're not actually saying anything different. It's just saying that this, since we're treating it with respect to as h approaches zero,
this thing we calculated, 2x plus h minus 3, is going
the change in y, essentially, right, because we've already simplified it, is going to be 2x plus h minus 3.
to get closer and closer to being just 2x minus 3. So what we've calculated here is called the derivative of f with respect to x. And to see what it means, let's go back to the graph of our function and draw in its derivative as well. Now we can see here that where the
Okay, so we had this original function, which was this, and then we calculated it based off of. Okay, so let's try this again one more time, all on our own. Or actually, let's an example to find the derivative of. Let's try to find the derivative of something else. Okay, so simple, right? Let's follow the same exact methodologies and everything that we did, and try to get to where we got to. So first you start with f of x, and then you want to go to f of x minus, or sorry, plus h minus f of x, right? So this in itself is going to turn into x plus h, sorry, this is going to turn into x plus h squared minus x of h, or sorry, yeah, just x squared, because this is just y, and we're saying plus x. So then you're saying x plus h, x plus h, which gives you x squared first outside plus xh plus xh outside inside, then last plus h squared minus um, x squared. Right. So now, to me, we go ahead and cross these first terms out, and then you're left with 2xh plus h squared, so which you can divide by h and get yourself x plus h, which is the derivative of, um, or is it 2x? Well, no, because you're really saying the x equals as the limit of h approaches 0, it's going to be 2x plus h. Or is it just 2x? I think it's just 2x, actually. Yeah. So this to me would just be 2x. So let's see what we're looking like. Ha ha ha. Wonderful. All right. Let's get back to it.
Derivative is 0 corresponds to where our function has 0 slope.
Okay. So now we understand that if we get the derivative where x equals 0 is where the function has 0 slope.
And
The,
with
the parent function has 0
the
slope.
derivative is negative, that's where the function is sloping downwards, and so on.
Mm.
So the derivative is the super helpful thing that tells us the exact slope of our function at any input value. Let's quickly go into our code and create a little function which returns the derivative we just figured out, and then we can
Okay. So, so now coming back to this, I completely understand what's happening. This is just he's just hard coding the derivative into place after we solved it by hand.
replace all the stuff here with just a single call to that derivative function, like
Yep,
so.
yep, makes
Then to
sense.
test it, let's try drawing the slope again, and it works perfectly.
Hmm.
So we've managed to make the slope calculation more accurate and more efficient, with the only downside being that we do have to actually figure out the derivative of whatever function we're using.
Yes.
Just as another quick example, here's that function we used earlier when we were thinking about gradient descent, and here's its derivative. And we
Do I dare try it? Do I dare try it? I don't think I need to. We understand what it's
can
doing.
see again how the derivative tells us exactly what the slope will be at any input value. Or put another way, how sensitive the output of the function is to a change in the input.
Mhm.
Okay, so to figure out how all of this is going to actually help us, let's consider a ridiculously simplified network that has just 3 nodes connected by 2 weights like this.
Okay.
And let's write out quickly how this works. So the input node receives some input value, let's call that activation 0,
Okay.
and we then calculate the weighted input, Z1 for short, which is just the input multiplied by the weight plus some bias value.
So let's try to get a refresher here. So with the node, your node is going to have an activation function, which it'll get the previous input, right? Uh, and then the weight for the connection to the next one, plus the bias to that connection, times the activation function is what's going to be the weighted output or the weighted input for this next node, right? Z should go here.
Next, we calculate activation 1 simply by passing the weighted input into our activation function.
Wait,
We
wait,
then do
wait. No. What? Activation 1 equals. Oh, okay. So what's A?
weighted input, Z1 for short, which is 0.
I see. Labeling the input as activation is a bit strange since it hasn't been through our activation function. I understand. So really, this is like, are we labeling it A0?
And we then get the input, the weighted input, some input value, let's call that activation.
Okay, so A0 is actually just the input value. So really, let's call this input 1. Gets put into the node along with so I times W plus B. equals z, which is the weighted input for the next node, which then has its own true activation function, right? Which ingests the input of z, right? So now z2 or 1, I guess you could say, is equal to the activation function of z, and then that gets put into the weighted input for node 3, which should have an activation function for z1, which turns into z2, is my understanding.
0, and we then calculate the weighted input, z1 for short, which is just the input multiplied by the weight plus some bias value. Next, we calculate activation 1 simply by passing the weighted input into our activation function.
Hmm.
We then do the same thing to calculate
So you, okay, yeah, yeah, yeah. So you get now,
z2 and
you get the weighted input to go into the next node. And then once it hits that next node, you're using an activation function, which I'm kind of fuzzy on if I'm being honest, but I understand it's a function used on utilized on each node to kind of help the data be more usable. And then after you get, so after you put the weighted input, so here's the steps, right? You have first just raw input, okay? It's that first node. This raw input then turns into a weighted input by taking the input, multiplying it by the weight of the connection to the next node, and adding a bias to it. And so now this weighted input lives here. And as it gets ingested into this next node, it goes through an activation function. So this A is a function. And then this now becomes the new weighted input, this new A for this next function. So then you say, okay, well now Z equals A, this child here, times W plus B. This is going to be Z1 for you. And the same concept, you have another node. So this Z1 now becomes the the input to here, which runs through the activation function of Z1. And then now for Z2, it is equal to A, which A is coming from here, times W plus B.
finally a2. We can now evaluate the network by calculating the cost, so we just use the cost function and pass in the
All right. So after all of this, now we calculate the cost of this run, which he says is simply passing the cost function. But what is that?
output activation value, along with the expected output for the current training sample, or y for short.
Yeah.
Now, if we think back to this horrifyingly inefficient gradient descent code that I wrote, remember what we're trying to speed up is this calculation here of how sensitive the cost is to a change in any particular weight or bias parameter. So let's say we want to calculate that value for weight number 2 over here. Instead of approximating it, we've seen recently that we can actually get a more efficient answer by calculating the derivative.
Uh-huh.
And I'll write this with these fancy curly d's since we're dealing with functions with multiple variables now. Anyway, this might look a bit confusing to calculate because we're trying to figure out how W2 affects the cost,
Hmm.
but it isn't one of the cost function's inputs. So to unravel this mystery, there's one final calculus concept for us to contemplate today: the chain rule. The
And
chain rule
that
tells us
will be a great stopping point. Um, we went really in depth into derivatives, how to calculate them, sort of get some basic calculus refresher. Do have to get to work though, so it was wonderful. And tomorrow we will get into the chain rule, partial derivatives, and hopefully back propagation if it's not too much. Um, and then from there we can get back to coding, digital recognition, doodles, all this other stuff. Wrap up the video and then get back to doing what we do best and actually building, actually creating. All right. So have fun. Have a good day.